I'm Roland Minton. These are some of my favorite math stories. In this episode, mathematics is magical. A lot of magic tricks are based on the convergence of a process. Then the audience can begin the process anywhere they like, and the magician can know exactly what the conclusion is. A full proof of the mechanism behind the calculator trick in this episode requires calculus. We'll look at that very briefly. But the result is surprising, and the trick can be executed in more than one interesting way. This trick is a variation of one I learned from the great Art Benjamin. Check out his TED Talks, great courses, and mathemagic books. They're all great. Now, you need an assistant to have a calculator. Most phones will do that carries at least 7 digits. The only way the trick might not work is if there is a crucial round-off error. So, have your assistant start with a 3-digit number with no 8s or 9s. I usually tell the assistant to construct the number from 3 different digits. The trick works with repeated digits, but someone choosing 777 or 000 takes a lot of fun out of the trick. Then we go through a number of odd calculations. Magicians like to be punny. Multiply by 9, add 7, divide by 7, divide by 9, divide by 11, divide by 13. The result should be a decimal, 0 point some stuff, and again we want at least 7 digits. We are only interested in the first 6 of those at first. So trick number 1 is tell me any 5 of the first 6 digits in any order you like, and I will tell you which digit you left out. For example, if I'm told 43047, I would immediately reply with, well, why'd you leave out the other 3? Or you can pretend like you're having a hard time reading the assistant's mind and take your time giving the answer. I often write the numbers down on a board, partly to help me remember them, but also because that's helpful explaining the trick later. A second trick is, tell me digits 4, 5, and 6 in order, and I will tell you which number you started with. For example, I might be told 430 and reply your starting number was 347. Trick number 3, I've never performed this one live, and it requires a calculator with a couple extra digits. After hearing digits 4 through 6, I can tell you digits 8 through 10. For example, I'm told the 430 like above, and I would reply digits 8 through 10 are 474. Alright, well how do these tricks work? They all depend on the final number in the calculation having a very precise form. In particular, for trick 1, the sum of the first 6 digits is always 21. Told 43047, the sum so far is 18, so the missing digit is 3 to make 21. If you're calm enough to add the numbers while they are being said out loud, you can give the missing digit as soon as you like. For trick number 2, the first 3 digits are always the 7 complements of digits 4 through 6, and they are the starting number. So the first 3 digits, given 430, find the 7's complement. From 4 we get 3, 3 plus 4 is 7. From the 3 we get a 4, 3 plus 4 is 7. And from the 0 we're going to get a 7. 7 plus 0 is 7. So 347 is the starting number. And this explains also why the sum of the first 6 digits is always 21. Pairs add up to 7, 3 7s makes 21. For trick 3, the final number is the first 6 digits repeated indefinitely. If digits 4 through 6 are 430, digits 1 through 3 are 347, the number is 347 430, 347 430, etc. So digits 8 through 10 are 474, exactly the same as digits 2 through 4. Of course, you could also identify any and all digits now. Digits 37 to 40 are the same as 1 through 3, and in this example would be 347. Of course, it is unlikely that your volunteer assistant will use a calculator with 41 digits. Now, why did I say 41? Well, this trick can be ruined if the last digit in play gets rounded up. The assistant's calculator needs to have a buffer digit to avoid this. Well, let's practice. If you were told digit 65421, what's the missing digit? If digits 4 through 6 are 624, what was the starting number? What are digits 8 through 10? So here's some answers. 65421 add up to 18, so we're missing a 3. Complements of 624 are 153, so the starting number was 153. Digits 8 through 10 are the same as 2 through 4. That's going to be 536. That's a pretty nice trick. Now that demonstration of how the trick works doesn't exactly explain why the trick works. I said that the answer is a repeating decimal with the original number giving the first 3 digits and the next 3 digits being the 7's complement of the first 3. All 3 of those facts are important. But how do we know that this will always work? So the answer involves a geometric series. We've been seeing a lot of those. So doing this calculation with numbers replaced by letters gets very messy. Let's do an example using a starting number of 634. I'm going to cheat a little bit by working backwards from the answer, but everything involves an equals, so we can meet in the middle and it's still okay. What I've claimed is that the calculations will produce 634143, 634143, and so on. This can be viewed as a geometric series in the following way. That first 634143 is equal to 634,143 divided by a million. The second 634143 is the same as 634,143 divided by, well, 1 with 12 digits, or 1 million squared. Then the third 634143 is 634,143 divided by a million cubed. So putting this all together with the rest of the decimal, 0.634143, etc., is equal to 634,143 divided by a million, plus 634,143 divided by a million squared, plus 634,143 divided by a million cubed, and so on. To get from one term to the next, we multiply by 1 over a million. So this is a geometric series with starting value C equal to 634,143 divided by a million, and a ratio of R equals 1 over a million. The formula for the infinite series is C divided by 1 minus R, so that is 634,143 divided by a million divided by 1 minus 1 over a million. Well, fractions and fractions are annoying. Let's multiply everything by a million. So on top, we've got 634,143. On the bottom, we've got a million minus 1, or 999,999. Now for some magic, I guess. 999,999 turns out to be 7 times 9 times 11 times 13 times 111. And if we pair up the 111 with that 634,143 on top, that division turns out to be exactly even. 634,143 divided by 111 is 5713. So our infinite series equals 5713 divided by 7 times 9 times 11 times 13. Now let's go back to the beginning where the magic would have started. So the assistant's going to start with 634, multiply by 9, and add 7. Guess what? That equals 5713. Then you divide by 7, 9, 11, 13, and you'll get the repeated decimal that we wanted. So now again, the explanation of why falls a little bit short. This works for 634, but does it work for all numbers? All you have to do is replace 634 with ABC, where each letter represents a digit from 0 to 7. The next 3 digits of the decimal will be 7 minus A, 7 minus B, 7 minus C. Then just repeat all of the above steps. Now you again want to start with the repeated decimal ABC, 7 minus A, 7 minus B, 7 minus C, repeated, and see what its sum looks like. In fact, that's how I made up the trick in the first place, starting with the result I wanted and seeing how to get it. But then maybe you're okay with me saying that I've done this and it works.